Heinemann Higher. Chapter 6 on differentiation, the mixed exercise 6S at the end. Question 10, which is find a maximum minimum value of this in a closed interval. But first a bit of history. So consider the graph of this, which we'll put here. So this is the graph, again, the typical two turning points of a cubic graph, only descending because of this negative term here. But what it's saying is this, it isn't saying, oh, what's the value of the maximum turning point or what's the value of the minimum turning point, because they only occur locally. That may well be a maximum in its neighbourhood, but when it ventures out into the big world, you're getting bigger answers over here. Same with that minimum. They may not give you the maximum minimums overall. So when it says, what's the maximum minimum value of this function in this interval, it doesn't mean what's the value of the turning points. No, it means what's the biggest answer you'll ever get if you draw the curtains on it, so that one side comes down to -2, the other side comes to 1, and you're just looking at that part of the graph. So you've got these parts here. Now normally what happens in a graph would be, looking at this little part here, if there's a curve coming along in a little interval, the biggest values should occur at the boundaries. They should be endpoints. The only time that they could be disturbed from the positions of maximumness or minimumness would be if it takes a wee twist in between, like in this part here. Now the maximums and minimums don't occur at the endpoints because this turning point in between, or I should say stationary value in between, exceeds one of them in its lowness in this case. Or here, the maximum minimum values don't occur at the boundaries because this maximum turning point overtakes one of them. But when you've got two turning points in between, something like this, well, just by them taking a turn in between doesn't necessarily mean that they'll exceed the boundaries. All that it means is that they're worthy of consideration as contenders for overall maximum and minimum values. So what you'd have to do is consider what's the values you get on the boundaries, the end values, and are there any stationary points in between? Because if there are, they could, but only just could, exceed either of those. And their actual natures don't matter. The only thing that matters is the fact that they actually exist. The fact that you then work out this to be a maximum doesn't then prove that it's going to be a maximum overall, only that it's worthy of consideration. So when it comes to a question like this, I'll need to figure out the values for this interval. I'd have to consider what do I get at -2, what do I get at 1, and those would be my answers unless there's a stationary point in between them. And if there's a stationary point in between them, then that's worthy of consideration. But I don't need to show the table of signs or a nature table, only the fact that I need to consider it and test it against the other two. So back to this. Let's just check if there are any stationary points in that interval. So I'll differentiate it. 6x minus 3x squared. I'll check for these stationary, but I'll not call them points here because it's talking about overall values. So I'll check for stationary values by saying I'll get a stationary value if that derivative is ever equal to 0. If 6x minus 3x squared ever equals 0, well, that's an easy one because I've just got common factors. 3x can come out, leaving me a 2 minus an x, which means something happens at 0, which is in the interval, or something happens at 2, which is out with the interval. So the only contender is x equals 0. X equals 2 could give a massive answer, but I wouldn't care because I only want to know between -2 and 1. So there's only 3 points then that need consideration, or 3 values of x that need consideration: -2, 0 and 1. Not x equals 2 because that's greater than 1. So my contenders are f of -2, so feeding -2 into that, so it's 3 times -2 squared minus -2 cubed, so that's 412, and that's going to be plus the 8, which is 20. The function at 0, which is just going to be 0, and the function at 1, which is going to be 3 times 1 squared minus 1 cubed, which is 2. And then I just have to now examine my candidates for the largest and smallest. The largest is this one here at 20, the smallest is the one here at So if the question says what's the maximum minimum values, I'll say this now. I'll have to put it up here. Maximum value of the function is 20 when x equals -2, and the minimum value of the function f is 0 when x equals 0. And that's all I need. No table of signs, because I'm not even really thinking about a graph. I'm just thinking of this numerically as a function. Its maximum values and minimum values should occur at the endpoints unless there's some stationary value between them, and there was, and then just consider what it is. We don't just demonstrate it's a maximum minimum, consider what it is and compare them against them to see if that could overtake one of them. So there it is, question 10.